Hey, what's up, guys? Okay, so yeah, so in this video that I'm going to prove this Mobius inversion formula. Why I'm going to prove it? Because this formula is like very common that in the analytic numbers theory or whatever, like I already see a lot of time. And so I want to make the video that so prove it and explain some details. And I hope you guys subscribe to my channel. Okay. And so let me just write down, right? So the classical version is yeah, so we will prove the classical version. So if you take g of n, which is f of d, where d is divisor of n or factor of n. Okay, so let me just write down. So this notation, d this so this means that d is integer, d is greater or equal to 1 and less or equal to n, and the d is a factor of n. Okay, so for example, when I say D6, this set will be just 1, 2, 3, 6. Okay, hopefully it's easy to understand. Okay, so G of 6 will be just F1, F2, F3, F6. Okay, so when I write G of n as this, then there's inversion. So this is the same as like Fourier transformation over finite field continuous Fourier transform, or however there are a lot of or Merlin transform. There's a lot of kind in formula in mathematics that you can transfer this to. Okay, so your f of n can be turn it back. You can write as g n divided by d by mu of d, and the d divides n. And this the amazing thing is that this all the mystery comes from this mu is called Mobius function. Okay, so let me explain Mobius function. So so this is mu called Mobius function. So the definition is mu of n will be 0 and 1 or minus 1. 1 if n is the product of distinct primes. The number. Oh, okay, maybe this is a bad notation. Let me just. So if n is a product of distinct prime, let's say the number of distinct prime is k, then this is defined to be minus k, minus 1 to k. Otherwise, it's 0. Okay. So for example, let's say mu of 6. So 6 is 2 and 3, right? So there are two distinct prime, so it's 1. And let's say mu of 4. 4 is 2 squared, so it's 0. Okay. And the 10, 2 times 5 is just 1. And then this day is 30, 2 times 3 times 5 is minus 1. And the notation is that mu of 1 is basically 1. Okay. So yeah, so this is the definition. And the important formula that we basically, if you want to prove this Mobius, this inversion formula, the most important formula, or basically the lemma is the following. If you take all the element d, and d is a factor of n, then this will give you delta n unless n is 1. Okay, unless n is 1. Okay, so let me explain here. So the lemma that we need is the following: mu of d dn. This is n1. Okay, so maybe let's try an example so that give you a feeling. So let's say n is 6. So you have your 1, 2, 3, 6. Right, so it's 1 minus plus minus 1, right? 2. So each prime a prime, right? We only have we'll give you minus 1 because there's only one distinct prime. Okay. That's minus 1. 6 is 2 times 3 is 1. So 0. Okay. And then you can try a lot. But basically what I want to say is that in order for this term to be non-trivial, only n is 1. So this is usually if you have this kind of formula that you can get the delta function, right? As a Fourier transform, you have some delta function so that you can do the inversion. Okay. So this is somehow like very similar in any kind of mathematics. right? If you have some delta identity, then you can do the inverse transform. And let's quickly do proof, right? So the idea is that I only care about if I want to do this summation, right? I only care about n is the uh okay. So obvious that if n is one, that this is true, right? So I only need to care about n equal to 2, and I only need to care about that. I only need to care about the distinct prime, the factor with distinct prime. So for example, as n is a p1 m1 p2 m2 up to let's say pk mk. Then I only the possible d such that the left hand side is non-zero. For example, if there's only one prime one prime factor part will have like p1 p2 up to pk. And if there are two prime, that I have like P1, P2, P2, P3, P1, P3. Okay, something like this. Okay, and if there are factor has three distinct prime, where P1, P2, P3, and up to like the K prime. So K prime is only one element, P1 times up to Pk. So we just count the number of it, right? So the number of this guy has K, and the number of these guys like K choose 2, K choose 3, and up to like what? Okay, and there are factor. Sorry, there are contribution. So contribution of single prime will give you -1. This will give 1, -1. Okay. So if you just write this down, mu of d will be just the number of d is, let's say k from 1 to n, up to 0, right? There's a still 0, 1. So this is, yeah, basically there's. So I should say k start from 0, right? For when k equals 0, then the contribution is 1, just 1 mu of 1. Okay. So this guy will be just k choose. Sorry, this is not it. Oh, sorry, bad notation. Right. So let's say n is the p1 m1 up to pk and k. So this term will give me let's say n choose alpha. Alpha start from 0 to k, and -1 to the alpha, right? Because each alpha means that the other alpha prime factor. And by Mobius definition, the alpha prime factor will give you -1 alpha. Okay, so you get this. This is 0. Okay, because this is just the binomial theorem, right? The binomial expansion. So it's 1 plus -1 to the sorry, this is k. Okay. Unless k is 1. Sorry, unless k is 0, right? So we show that unless k is 0, which means that the number is 1. So this means that we show the proof. We just finished your proof. Okay, so now we already have this theorem. So we are going to using this theorem back and prove the Mobius inversion formula. So let's quickly see the formula. Okay, so let's write down the proof. So theorem f of n is dn mu d, and then g of n is dot dot dot. Sorry, this is what I'm doing. So this is GF. Okay, so we want to prove this. Okay. So the proof is basically. Okay. So the proof basically just write down everything. So let's say we plug this into second. G can be the definition, right? So we just plug into second. So let's write down. Let's write right hand side will be just dn mu d. So gn divided by d. Okay, so this comes the so let's say we take let's say d prime is n divided by d, and f d prime. Okay. Okay, so here comes the part, right? Here comes the trick. So this is n, right? So this summation means that I take d prime, where is okay. So I should first take d, right? I take d, and then this is n divided by d, and n divided by some integer, right? And I take d prime of it. And if you think about it, this is the same as you take any two numbers which products the factor of n. So here comes the trick. If you need to think a little bit, basically this means that you can take CD times n. C times D is a factor of n, right? Any two of it is true, is okay, because whatever it is, you n divided by D, the rest you just take C, right? So if you see this, then the proof will be this. So you get mu D, and then this is just take C, right? So you take any CD pair such that the CD divides n, and you just mu D FC. Okay, so if you see this, then finish your proof, right? Because you just pull out this, and you take mu of D. Okay. If you want, if I change to this, then if I change to this notation, right? Then this I need to fix C, and wherever I fix C, then it becomes n divided by C. Okay. So this means that if I do this, I will just take C is a factor of n, and wherever I pick C, I pick another D. Okay, so it's D divided by n. D divided n to C. Okay, and finish your proof, right? Because this guy is basically the formula, the lemma, which is C1. So I get Cn or C delta n divided by C1. So in order for this guy to be true, that NC need to be 1, right? So this means that this means the f of n. Okay, so this proves the Mobius inversion formula. Okay, so one application which is important, this is a little bit non-trivial, is to show that if you take Euler phi function, then you should be able to prove this. If you take d divides n phi of d, this should be it. Okay, so this leave as exercise. The proof is a little bit you need some time, but probably it's not so difficult. Okay, see you guys next videos.